But what I'll be talking today about is how can we design PFAS structures so that we don't have to worry about what unknown is out there and what kind of chemical architecture we can have within this molecule so that it will break down once it's in the environment while still maintaining that high function. Okay, so anytime we talk about PFAS, we have to talk about those OECD guidelines. With these new guidelines, there's a huge number of PFAS that fall under this category with a lot of diverse functional groups and uses. And whenever you have this huge data set of structures, they kind of are coming from a point of all these different uses. So we've highlighted different firefighting applications, surface protectants, Teflon frying pans, and kind of cosmetics and whatnot. So all of these structures are unique to those specific applications, and all of them are taking advantage of those strong carbon fluorine bonds and some functional head group, typically that's providing some surfactant or kind of polymer applications with that. So yes, we have a wide range of structures. However, often PFAS does get broken down into specific classes. And so we have our carboxylic acids, sulfonic acids, in addition to some telomer stuff, all of which varying lengths. And so it's helpful to look at PFAS in groups like this because then there are similar kind of behaviors within the same functional group. However, between groups, it is vastly different. And then also on the right side here, we have Adana, F53B, and Gen X. These are kind of those replacements, replacing some of those notorious phased out structures. And what you can see here is we start introducing some heteroatom linkages, so some ethers, in addition to chlorine atoms and whatnot, to try and change the properties of these molecules to avoid the bioaccumulation effect, as well as still retaining that high functioning. And so, as I mentioned, the kind of bad guys, or what have really given PFAS the forever chemical name, are these PFOA and PFOSs, which have been banned and heavily restricted for a very long period of time now. As we saw at the last talk, they're still detected in quite high frequencies, but they've been phased out. We've replaced them with some newer structures like Gen X, Adana, and whatnot I was just mentioning. So industry is shifting to more functionalized structures in addition to smaller structures to, again, avoid that accumulation persistence. However, we can still detect a lot of these structures in the global and like remote environments, as they're still quite persistent in the environment. They just, at certain times or in certain cases, do have reduced bioaccumulation. However, some of them are still as toxic or potentially as toxic as their predecessors. And so, how can we kind of take a look at these specific structures and formulate an idea of what we can introduce into these Lego sets of molecules to stop this cycle of replace it, that's not great, replace it, and whatnot. And to this point, we don't have a golden solution yet, but hopefully that's where my research comes into play. So I've had the unique opportunity to have these 5 hydrofluoroether alcohols. So these would be building blocks for a surfactant. The top one is actually in production in the market at the moment. The others are kind of proposed changes to those to try and get an idea of what is specifically within this cool structure, what is causing it to behave the certain way as it does, because studies have shown that this does degrade into that C3 acid, but what kind of these different functional groups, what is leading to that and what has the most effect. So what's fun about these structures is we have different heteroatom linkages. So we have a lot of thioethers in addition to some ethers and a structure without the heteroatom linkage. And in addition to that, we also have longer terminal chains. And so with all of these factors, we can get kind of a full matrix of what specific change can result in what specific fate in the environment. And as a final kind of point is we have these hydrofluoroethers right here, hence the names, whereas that is a CHF, kind of introducing a weak point in the molecule to potentially down the road have some degradation and avoid that long-term persistence. I know with these PFAS SciEx talks, we talk about the life cycle, and then we have that really fun diagram and hopefully Lego sets that Francis has talked about quite a bit. And we know that once PFAS gets introduced into the environment, it can get into all these different compartments. often water, soils, and humans. However, when a chemical is used, whether it's in like cosmetics, nail polish, or in factories and whatnot, eventually it will get released and ultimately end up in many different compartments, but two very important and characteristic compartments are the atmosphere and in treatment plants. Because if it's volatile, it'll get into the air and have some unique transformative capabilities. And if it's in the treatment plant, it's washed down the sink, and that provides a whole new host of potential transformation pathways and unique capabilities for these molecules. So first, looking at the atmosphere, we used a really cool atmospheric chamber at the University of Toronto in John Abbott's lab. This work that I'll be presenting here is actually recently just published. The title is the title of the talk, so you can go find that there at ES&T. However, in these chambers, we're able to mimic different environmental conditions to kind of get an idea of what would happen once it's out in the environment. So our experimental setup is we can introduce our chemicals through either a perm tube or direct injection. We bubble hydrogen peroxide into the chamber and hit it with UVB light. That makes OH radicals, which are the dominant oxidizing species in the atmosphere. So if anything's reacting up there, it's likely from these OH radicals. And then we'll be monitoring all the species within there, either on the iodide time of flight SIMS or the PTR TOF mass spec, both mass specs, both time of flight instruments. We've employed this PTR TOF to get a better measurement of these aromatic species. We've used these as a positive control to get relative rates of all of our unknowns. Toluene, xylene, trimethylbenzene, these species here are really well established. We really know how fast they react and what happens. And so based on how those react in these chambers, we can get an idea of what's going on with our unknowns. So we used those to really hammer out this FeSO, this longer thioether alcohol, to get very confident with that OH rate constant, how fast it reacts with the OH present in the bag. But what's fascinating and really powerful about this relative rates method is it's an in-experiment control. And so whether you have different conditions, the temperature is a little bit different that day, have maybe more radicals, we know the species, the positive control on the x-axis is reacting at a certain rate, and so it'll always normalize out. So we get these beautiful, beautiful linear curves comparing these unknowns to the reference that we've established. It's a little busy here, but they just wanted to kind of show those beautiful, beautiful linear relationships. These KOH rate constants, what do they mean? Well, ultimately, they're going to correspond to lifetimes in the atmosphere. So how many times or how long will it take for this kind of chemical to be reduced by a certain amount? So we get this clear relationship that these thioether species react with lifetimes of 4 days and 5 days are reacting much faster than these other species. And then interestingly enough, within them, we also see that there is a length dependence. So this longer FeSO reacts a bit faster than this methylpheso or mefeso. Just a slight difference, however, it is noticeable and it is statistically significant. So that's great. We know what reacts faster, but ultimately with PFAS, it's only half the story. It reacts faster, that's great, but what does it turn into? Are we getting any persistent products? So back to the same experimental setup, throw the chemicals in the bag, OH radicals, monitoring it. But what's really, really cool about using a time of flight SIMS mass spec, specifically with an iodide as the reagent ion, is it's very sensitive to these fluorinated alcohols. And so we can monitor that at a high frequency phone call. Get a high frequency measurements of these species. And then also additionally, it is providing high resolution data. And so we can get really cool structural elucidation of these species in a live manner throughout this experiment. So this is just some quick time traces, and we get to see some loss of intermediate products, productions of terminal products, and so we can really see this life cycle as these chemicals are in the atmosphere. They're reacting into second and third generation products. Get a really cool kind of picture of the fate of these chemicals. Now this is qualitative, but it's interesting comparing between them, apples to apples, pink to pink, black to black, red to red. what is producing more and at what different time points to kind of get an idea of, as it's shortening down, what points is it kind of stalling out in that degradation. What's really fascinating is these thioether species, so the longer and the shorter ones, we get this explosion of products, first, second, third, fourth, in addition to these high resolution identifications of these. So we're quite confident in these that these are present. Lights go on, they go up, and that accurate mass. But it is cool seeing certain species are able to produce these shorter acids. Don't worry too much about the names. I just kind of wanted to highlight the power of this technique, as well as some really cool, thorough life cycle as these things react in the atmosphere. So yes, a lot's going on with these thioether species. But like any good analytical chemist, we need numbers. Colorful traces are one thing, numbers are another thing. So back to the experiment, same setup, throw it in, react it. But this time we're going to trap that air as it comes out in water, pretty much aqueous bubblers. When a big loss mechanism of acids, perfluorinated acids, in the atmosphere is wet deposition. So they'll get rained out pretty much. And so we're just trying to mimic that. Things are reacting in the atmosphere. And if it got passed through water, it would be trapped. Then we can use some LC-MS triple quad, get some quantifiable numbers with that. So we took these bubblers and analyzed it in two different ways. So the first way was with an LCMS, getting some targeted quantification, some nice numbers. Additionally, we ran some ion chromatography to try and get some fluoride measurements to see if we're producing any fluoride, if these are fully mineralizing. So here's some kind of harder, like more established numbers to complement those qualitative data that we talked about earlier. The shorter species, they're producing different smaller acids. What was quite interesting here, and I'll highlight a little bit in a little bit, is the thioether species are able to produce that immediate carboxylic acid in the red. But more importantly, this blue is significantly shorter. It's this PFECA right here. That is a very small fluorinated acid. And so that will not accumulate in mammals at all. However, the ether species, they kind of stall out. This red is just that immediate carboxylic acid. So the alcohol getting oxidized to the carboxylic acid there. And that does have more persistent potential when in the environment. But again, we know that these thioethers react faster. So what are they producing? As I mentioned, we've got these kind of the blues, that shorter acid, which is ideally what we would have when things break down. But what I wanted to kind of talk about here is this mass balance in the dotted line, and kind of bury the lead a bit here with the brown curve of fluoride. But we noticed as we were running these that we we're getting like terrible or not great mass balance of this shorter methyl FeSO. And where was it going? We were catching great mass balance of everything else, looking for the different species, but what was going on? And so we went back to that fluoride measurement that I mentioned earlier. And it was really, really cool because we could see as the time went on, as the dose started reacting away, this yellow curve here was that methyl FeSO, that shorter species that we were not able to account for earlier. And so originally we were getting like 20-30% recovery. And so once we were actually taking into account fluoride production, so as it's chewing through, it's reacting all the way down to complete mineralization and leaving only fluoride in its wake. And so we were able to get much better mass balance and able to document some mineralization of PFAS chemicals, which was really, really cool. And so summing up the atmosphere in itself, we got yes, thioethers, these S's, they react fast. Used and whatnot, because it does have the capability to fully mineralize. But back to that life cycle. So we've dealt with the atmosphere. What if things are entering into this treatment plant? Employ different techniques to kind of clean the water before we release it into surface waters. One big mechanism is through biodegradation. So it's the sludge, doesn't smell the greatest, but it has these microbial communities that can chew up and break down different man-made chemicals. And so through some not very glorious sampling and acquiring the sludge, we set up different microcosms, which are just a fancy way of saying bottles with the sludge, put vitamins, minerals, and air into it to keep those microbes happy, and watched as these different species kind of break down. As good analytical chemists, we have our positive controls, which were interestingly mentioned earlier, these FTUCAs. They are reacted quite not fast, but it's well documented how fast they do react, and they are acted upon by these microbes. And so it's a good positive control to make sure those little bugs are happy. In addition, some abiotic degradation, so just water. Are these breaking down by just putting it in the minerals themselves, or are they partitioning into the to the sludge, and so we're losing it that way? Just want to be very, very thorough with any losses we observe. And so with that in mind, when we dose these chemicals, it's really cool because we can see, yes, we loss away of these alcohols, but the biggest difference here is this black curve, which is the profio, which is this chemical down here without that functional group, in addition to that ethanol CH2OH group there that is obviously loved by those microbes and chewed up in itself without not much is going on. You can also see a bit faster of these yellow and red, which is, again, those thioether species. That's a little bit closer. Looking at an individual species in itself, you get some nice loss curves, production of acids, that's all fun. However, what was interesting is we start seeing these small acids pop up again as time's kind of going on, near like 20-ish days, which was quite cool. And we only saw them in these, again, broken record, thioether species. So the shorter and longer ones are producing these acids. That was not present in any of these other species. So if that's kind of the end result, is there any more potential going on? And due to these bottles being kind of contained and experimental issues, we couldn't continue this going past about 27 days. So start over. But this time we're going to introduce those small acids and see if that's the end of the road. Same setup, throw those acids in addition to that sulfonate, because we noticed that in the atmospheric study. So might as well throw it in as well. Positive controls, negative controls, all that good stuff. And here we're able to run it for a lot longer. But interestingly, we found no observable loss in these microcosm systems for these small acids. They cruised along. The gray is the positive control, that FTUCA, just showing us that the microbes are happy, they're doing their thing, they're able to transform fluorinated compounds. However, treatment plants don't just maintain their effluent, it goes out into surface waters. So then what happens? Again, how can we extend this environmental fate, this big picture of things? So when it gets released into surface waters, there's a potential for photofate or secondary photolysis reactions to occur. That's just simply the sun hitting surface waters, and the components of these surface waters, like nitrates, organic matter, carbonates, are able to produce radicals and further transform things, albeit at a much slower rate. So we introduce these small acids as they would effectively get released into Lake Ontario. And we've included some perfluorinated species that actually have been kind of talked about earlier in these talks that are detected in the environment as byproducts and whatnot, just to compare, okay, if anything's going to happen, it's going to happen at these H's, these CHFs. It's the only reactive site there. These negative controls do not have that. So if we're seeing any loss between the two, it's going to be that H. And again, measuring everything with targeted mass spec triple quad. So with artificial surface water, this was kind of a more extreme incident. And so we introduced a lot of nitrate and very little carbonate and organic matter, just to see these are the best conditions for secondary photolysis, production of those radicals to chew anything up. Compared that with Lake Ontario, where the Ashbridges Bay, the treatment plant that we got the sludge, does release into Lake Ontario. So this is a truly real world example. We're able to run it for a bit longer, and you start to see a bit difference as things are going on. These brown curves here are atrazine. That's just a positive control to make sure that our system is working, that it's producing reactive species the way it should. And if we don't see any loss, that we know it's not the system, it's the molecules. So at long periods of time, we can start seeing a bit of a difference with these blue and green traces, which are our degradation products that we found. And the purple and yellow are these perfluorinated species. So we're saying next to no loss with those over time, but we are seeing a bit, maybe give it a couple more days, maybe in a couple more weeks, and that difference will be more observable. But in the artificial, where things are a bit more drastic, there are conditions like this in the environment. However, it's a little bit more beneficial than Lake Ontario, and we do see these differences. And so we're able to conclude that yes, there is reactivity at these CHF groups, and yes, they're able to react further away. And once those kind of CHFs, specifically the H, is reacting off, that molecule will fully break down and completely mineralize. Again, not something we hear much about with PFAS research. So putting that biodeg water treatment plant stuff together is yes, like those thioethers do react a bit faster, but they do react to a greater extent. We get to see an increased shortening of these products into these very, very small species, which do not further biodegrade. But when released into the water, there are opportunities for these short acids to fully mineralize, resulting from these shorter fluorinated alcohols, with that short terminal tail, giving the potential, again, to fully mineralize with PFAS. So PFAS, are we going in the right direction? We don't want to keep producing things that will make small acids that will reside in the environment forever. So what can we do? So with these last 2 years of work that I've done, kind of showed that these inclusion of these thioethers are incredibly beneficial for environmental degradation. In addition, these CHF groups that we're starting to see a bit going on in industry applications, specifically Adana has one. But if they're at the terminal end of this molecule, as everything's done, there is still opportunity for further degradation to really get PFAS to be reactive rather than recalcitrant. So I'd like to thank everybody who's worked on this project, specifically Steph Schneider and John Abbott for really helping out with the atmospheric work. I'd like to thank NSERC and Merck for some funding and the Maybury Research Group overall for all the help.